Hi, geometry scholars. This is Mrs. Payne. We're in 9.5 now. So last time in 9.4, you learned about the tangent ratio. There's two other trigonometric ratios I'm going to introduce you to today. They're called the sine and cosine ratios. And if you've never heard of them before, these are again going to be super important, but it's the same concept. Right triangles only, legs and hypotenuses. We're going to talk about the adjacent side, the opposite side, and how we can use those other ratios of sides to solve problems. So we're not only going to do regular sine and cosine, but we'll also do it in special right triangles, as you can see in the objectives, and then solving real life problems. And believe it or not, it really is super useful. So have your calculator ready and the notes ready to go. So these are other vocabulary words I'm going to expect you to know: sine, cosine, and angle of depression. Without further ado, here we go. The sine and cosine ratios are trigonometric ratios for acute angles, those are the small ones, that involve the lengths of a leg and the hypotenuse of a right triangle. So this is how we're going to define them. If we have ABC, a right triangle with acute angle A, so we're only looking at A, the sine of angle A and the cosine of angle A is written as, and we abbreviate them to SIN and COS. You can look on your calculator, that's what it looks like, are defined as following. So we're looking again at angle A. The sine of A is equal to the opposite leg divided by the hypotenuse. So if you were going to label it, it would be BC over AB. That is sine. Sine is opposite over hypotenuse. If you want to actually find the cosine, which is a different name of a ratio, then you're going to do the adjacent leg length divided by the hypotenuse length. So that would be AC divided by AB, as you can see here. That's all there is to it. It's just a definition. Learn it, love it, know it. So now we're going to use that, okay? We're going to find sine and cosine ratios. Here's your first example.
Find the sine of angle S, the sine of angle R, the cosine of angle S, and the cosine of angle R. Write each answer as a fraction and as a decimal rounded to 4 places. Solution. First, find the sine of angle S. The sine of angle S is equal to the length of the leg opposite angle S divided by the length of the hypotenuse, which is equal to RT divided by SR. Substitute 63 for RT and 65 for SR. So, the sine of angle S equals 63 65ths, which is approximately equal to 9,692 10,000ths. Next, find the sine of angle R. The sine of angle R is equal to the length of the leg opposite angle R divided by the length of the hypotenuse, which is equal to ST divided by SR. Substitute 16 for ST and 65 for SR. So, the sine of angle R equals 16 65ths, which is approximately equal to 2,462 10,000ths. Now find the cosine of angle S. The cosine of angle S is equal to the length of the leg adjacent to angle S divided by the length of the hypotenuse, which is equal to ST divided by SR. Substitute 16 for ST and 65 for SR. So, the cosine of angle S equals 16 65ths, which is approximately equal to 2,462 10,000ths. Finally, find the cosine of angle R. The cosine of angle R is equal to the length of the leg adjacent to angle R divided by the length of the hypotenuse, which is equal to RT divided by SR. Substitute 63 for RT and 65 for SR. So, the cosine of angle R equals 63 65ths, which is approximately equal to 9,692 10,000ths.
So one thing you should notice about this is the sine of S right here is the same thing as the cosine of R. See how they both came out to the same ratio? And the sine of r is equal to the cosine of s. So you can solve problems more than one way, and we will practice doing that. So in example 1, you notice that what I just said, this is true because the side opposite angle S is adjacent to angle R, and the side opposite angle R is adjacent to angle S. That relationship between the sine and cosine of angle S and angle R is true for all complementary angles from here on out. Now, if you do have complementary angles, that means they have to add up to 90 degrees. So we're going to define this relationship in these terms. The sine of an acute angle is equal to the cosine of its complement. And the complement is what makes up the 90 degrees. So the cosine of an acute angle is equal to the sine of its complement. So we're gonna fill these in our notes. If A and B are two complementary angles, then these statements are true. If you have sine A, that's equal to cosine of 90 minus A, or cosine B. If you have cosine A, that's equal to the sine of 90 minus A, or sine of B, and also the same this way. So that's an easy concept that we'll keep in our notes and in the front of our mind. Read more examples. Now, one of the things we can do is obviously rewrite them, and so you find out how to do that.
Write the sine of 56 degrees in terms of cosine. Solution. Use the fact that the sine of an acute angle is equal to the cosine of its complement. So, the sine of 56 degrees is equal to the cosine of the quantity 90 degrees minus 56 degrees, which equals the cosine of 34 degrees. So, the sine of 56 degrees is the same as the cosine of 34 degrees.
That's it. Okay. Next, what we can do is find unknown measures in right triangles, which, we always want to find x.
Find the values of x and y using sine and cosine. Round your answers to the nearest tenth. Solution. Step 1. Notice that x is the length of the leg opposite the 26-degree angle, and you are given the length of the hypotenuse. So, use a sine ratio to find the value of x. The sine of 26 degrees is equal to the length of the opposite leg divided by the length of the hypotenuse. Substitute x for the length of the opposite leg and 14 for the length of the hypotenuse. So, you have the equation, the sine of 26 degrees equals x divided by 14. To solve for x, multiply each side of the equation by 14. This gives you 14 times the sine of 26 degrees equals x. Using a calculator, you get 6 1/10 is approximately equal to x. So, the value of x is about 6 1/10. Step 2. Notice that y is the length of the leg adjacent to the 26-degree angle. So, use a cosine ratio to find the value of y. The cosine of 26 degrees is equal to the length of the adjacent leg divided by the length of the hypotenuse. Substitute y for the length of the adjacent leg and 14 for the length of the hypotenuse. So, you have the equation, the cosine of 26 degrees equals y divided by 14. To solve for y, multiply each side of the equation by 14. This gives you 14 times the cosine of 26 degrees equals y. Using a calculator, you get 12 6/10 is approximately equal to y. So, the value of y is about 12 6/10.
Now, if any of those steps don't make sense, or you don't know where the numbers came from, stop and do it again until it sinks in. Otherwise, it's very straightforward multiplication or division. And we're going to go on to the next one. This is another way to use, these are more examples that we'll do in our class notes together. So specifically in our special right triangles, our 45, 45, 90 and our 30, 60, 90, the card, they have specific values and they always show up that way. So this is something that, again, is going to be near and dear to your heart, and you should be able to follow this.
Find the sine and cosine of a 45-degree angle. Solution. Begin by sketching a 45-degree, 45-degree, 90-degree triangle. Because all such triangles are similar, you can simplify your calculations by choosing one as the length of each leg. Using the 45-degree, 45-degree, 90-degree triangle theorem, the length of the hypotenuse is the square root of 2. Now, the sine of 45 degrees is equal to the length of the opposite leg divided by the length of the hypotenuse. The length of the opposite leg is 1, and the length of the hypotenuse is the square root of 2. So, the sine of 45 degrees equals 1 divided by the square root of 2. To write your answer in simplest form, multiply 1 divided by the square root of 2 by the square root of 2 divided by the square root of 2. This gives you the sine of 45 degrees equals the square root of 2 divided by 2, which is approximately equal to 7,071 ten-thousandths. The cosine of 45 degrees is equal to the length of the adjacent leg divided by the length of the hypotenuse. The length of the adjacent leg is 1, and the length of the hypotenuse is the square root of 2. So, the cosine of 45 degrees equals 1 divided by the square root of 2. To write your answer in simplest form, multiply 1 divided by the square root of 2 by the square root of 2 divided by the square root of 2. This gives you the cosine of 45 degrees equals the square root of 2 divided by 2, which is approximately equal to 7,071 ten-thousandths. Notice that the sine of 45 degrees equals the cosine of the quantity 90 minus 45 degrees, which equals the cosine of 45 degrees.
Because of the complementary theorem that we've just learned in the last one. So you'll notice those are the same. Now we're going to do probably the same in 30, 60, 90. Okay.
Find the sine and cosine of a 30-degree angle. Solution. Begin by sketching a 30-degree, 60-degree, 90-degree triangle. Because all such triangles are similar, you can simplify your calculations by choosing one as the length of the shorter leg. Using the 30-degree, 60-degree, 90-degree triangle theorem, the length of the longer leg is the square root of 3, and the length of the hypotenuse is 2. Now, the sine of 30 degrees is equal to the length of the opposite leg divided by the length of the hypotenuse. The length of the opposite leg is 1, and the length of the hypotenuse is 2. So, the sine of 30 degrees equals 1/2, which equals 5,000 ten-thousandths. The cosine of 30 degrees is equal to the length of the adjacent leg divided by the length of the hypotenuse. The length of the adjacent leg is the square root of 3, and the length of the hypotenuse is 2. So, the cosine of 30 degrees equals the square root of 3 divided by 2, which is approximately equal to 8,660 ten-thousandths.
Which, as you can see, 1/2 and root 3 over 2 is not too bad. And then you can also, of course, find the other ones. For these are more examples. We'll do those in class. And then now we're on real-life problems. So in section 9.4, I introduced the idea of angle of elevation. Whereas if you're looking straight ahead on the horizon, anywhere up, it's that angle, that's the angle of elevation looking up. But if you're, say, on the top of a building, the top of a hill, and you're looking down, then anywhere where your eyes are looking straight ahead and looking down, that's called the angle of depression. Recall from the previous lesson, and so that's what we're going to do some problems now. Modeling with mathematics just means drawing a picture so we see what's happening.
You are skiing down a mountain with an altitude of 1,200 feet. The angle of depression is 21 degrees. Find the distance x you ski down the mountain to the nearest foot. Solution. Step 1. Understand the problem. You are given the angle of depression and the altitude of the mountain. You need to find the distance that you ski down the mountain. Step 2. Make a plan. Write a trigonometric ratio for the sine of the angle of depression involving the distance x. Then solve for x. Step 3. Solve the problem. The sine of 21 degrees is equal to the length of the opposite leg divided by the length of the hypotenuse. Substitute 1,200 for the length of the opposite leg and x for the length of the hypotenuse. So you have the equation, the sine of 21 degrees equals 1,200 divided by x. To solve for x, first multiply each side of the equation by x. This gives you x times the sine of 21 degrees equals 1,200. Then divide each side of the equation by the sine of 21 degrees. This gives you x equals 1,200 divided by the sine of 21 degrees. Using a calculator, you get x is approximately equal to 3,348 and 5/10. So, you ski about 3,349 feet down the mountain. Step 4. Look back. Check your answer. The value of the sine of 21 degrees is about 3,584 10,000ths. Substitute for x in the sine ratio and compare the values. 1,200 divided by x is approximately equal to 1,200 divided by 3,348 and 5/10, which is approximately equal to 3,584 10,000ths. This value is approximately the same as the value of the sine of 21 degrees.
So you should always check. Be in the habit. Again, these are more problems we'll do in our notes together. And there's exercises after that. So you're going to do your big ideas assignment. It should pop up like right now. It should be available. Okay, make sure you ask any questions you have of me.